Hi, I'm Zhijian Liu, and I'm currently a third-year PhD student at MIT working with Professor Song Han. Today, I'm going to talk about efficient 3D deep learning, and I will primarily focus on our two generations of efficient 3D deep learning models, PVCNN and SPVNOS. To begin with, how is 3D data collected and stored? 3D data is usually collected by the LiDAR sensors, which are usually mounted on the top of self-driving vehicles. Lately, collecting 3D data also becomes much easier. For example, the latest generation of iPad Pro and iPhone have both equipped with the LiDAR scanners. The data collected comes usually in the format of point cloud, or essentially a set of points, each of which is composed of XYZ coordinates and the corresponding intensity values. Thanks to these 3D sensors, 3D deep learning has raised increased attention as it enables more and more applications. It can be used in the robotic systems to parse the functional parts of the objects. It can also be used in the VR/AR applications to understand the indoor scenes, for example, to segment where the floor is and also where the chair is. Furthermore, it is also widely used in autonomous driving system to detect the pedestrians, cyclists, and the cars. All these applications are usually deployed on the results-constrained hardware. Otherwise, in VR/AR headsets, the users need to put on a backpack full of computers inside, which will, of course, be very heavy. For the self-driving cars, we might need to install a whole trunk of workstations to meet the computation demand of autonomous driving systems. To avoid all these, it is very important to design efficient 3D deep learning models that can run efficiently in these constrained scenarios. However, this is highly non-trivial due to irregular and sparse nature of the 3D point cloud, and also the additional dimension makes this even more challenging. Here we have compared 3D Minkowski net with 2D ResNet, both with similar network architecture and also similar network depths. We can observe that 3D model requires 4 times more training time and also 14 times more inference cost compared with its 2D counterpart. So in this talk, I will introduce some of our recent explorations in efficient 3D deep learning, and they are mainly from 3 perspectives. First, how to build an efficient 3D building block. Second, how to optimize 3D sparse convolution kernels. And third, how to design efficient 3D neural networks in an efficient manner. Let's first start with the 3D building block design. Designing efficient 3D deep learning building block needs to take the hardware into consideration. On the one hand, an efficient model should have more memory footprints because the memory operation is more than 20 times slower than arithmetic operations. On the other hand, an efficient model also needs to avoid the random memory access as it is much slower than sequential access due to the potential band conflict. Conventional voxel-based models are not scalable because the memory consumption grows cubically with the resolution. However, low resolutions will lead to significant information loss as multiple points will be bucketed into the same voxel grid, and these points are no longer distinguishable to each other. This leads to a dilemma here. With a single Titan XP GPU, we can only afford the resolution of 64 by 64 by 64, but in this case, more than 40% of information will be lost. To keep more than 90% of information, we then need to double the resolution to 128, but in that case, we need at least 7 Titan XP GPUs, which is not practically affordable for most users. Recently, another stream of models tries to directly process the point cloud. To apply the convolution, these models need to first carry the neighbors of each point, but unlike the 2D image pixels, these neighbors do not lie contiguously on the memory. For example, the neighbors of the first point might be some points in the middle or maybe at the end of the tensor. Therefore, organizing these neighbors requires considerable random memory accesses. Also, as the relative positions of these neighbors are not fixed, these models have to compute the convolution kernel dynamically based on offsets, which is also very expensive. After analysis, we found that up to 90% of their runtime is wasted on the structuring the sparse data, not on the actual feature extraction. Intuitively, we can capture the overall structure and find details of an object separately. With this specialization in mind, we propose a new primitive called Point-Voxel Convolution, or in short, PVConv. Specifically, we have a point-based branch that extracts the fine-grained individual point features to capture the details of the object. Without the convolution, this point-based branch is very efficient. However, this branch will be very similar to the one-by-one convolution in 2D CNNs. It is very efficient, but loses the capacity to model the neighborhood. We leave the convolution to the voxel-based branch where we convolve over the low-resolution voxel grids to extract the coarse-grained neighborhood information. As the voxel resolution is relatively low, this voxel-based branch can also be implemented very fast. In short, PVConv combines the advantage of point-based models, which is the small memory footprint, and the advantage of the voxel-based models, which is the regularity. Here we visualize the features extracted from the two branches, and interestingly, we found that the voxel-based branch learns to capture the large continuous parts, while the point-based branch captures the isolated and discontinuous details, such as the table legs. This phenomenon is well aligned with our design. PVConv is good at modeling smaller 3D objects and also small-scale indoor scenes. However, its voxel branch is still somehow constrained by the GPU memory. Therefore, it can only afford relatively very low resolution in this branch. Given a single GPU with 12 GB of memory, its resolution can be at most 128. But this is not sufficient enough for the large-scale outdoor scenes. In such case, some small objects will only occupy very few points. From the right figure, we can see that the pedestrian here only occupy like 4 to 5 points in the voxelized scenes, which is not enough for the model to extract very useful features. To tackle this issue, we have enhanced the PVConv for large-scale outdoor scenes. We replaced the dense voxels with the sparse 3D representation, where we only store these non-zero locations. So as the 3D point count is intrinsically very sparse, this modification can greatly reduce the memory consumption when the resolution is very high. We name this modified version as sparse PVConv or SPVConv. Similar to what we have done for the vanilla PVConv, we also visualize the attention of the point-based branch in SPVConv. Here we highlight the points with top 5% largest norm in the point-based branch, and we can see that it learns to capture the small objects on the road, such as the pedestrians and the cyclists. The bottleneck of SPVConv is on the sparse convolution, as the irregular sparse operations are not favored by the general purpose hardware such as GPU. I will then talk about how we optimize the 3D kernel to make it more efficient on GPUs. Unlike the dense convolution, the sparse convolution will only consider these points with non-zero values. For each output location, it will query all neighbors within the signing window to see whether they are non-zero in the input. For each non-zero neighboring point, we can then multiply its value by the corresponding kernel weight and then add it to the output point. However, it can be very inefficient if we conduct this operation separately for each output point. Therefore, a straightforward optimization would be to first find all pairs of such input and output points. We call these pairs kernel maps. After we find all pairs in the kernel map, we then compute the matrix multiplication altogether. The way to build a kernel map is to first build a hash table with the input coordinates as the key and the input index as the value. Then for each output point, we query the coordinates of its neighbors in a hash table to see whether it's non-zero. If so, we can then put this pair into the kernel map. We can parallelize this procedure for all output points so that it can fully utilize the hardware parallelism. With all this optimization and of course some other low-level engineering efforts that I will not go into details, we built a high-performance 3D sparse convolution computing library. We call this Sparse. Compared with the current fastest library, Minkowski engine, which is from NVIDIA, we are able to achieve a roughly 2 times measure speedup. And we have also made this library public, so feel free to try it out. Now we have covered how to design an efficient 3D building block and how to make it run fast. With all this, designing an efficient network architecture is still challenging because we need to carefully adjust the network architectures, such as the channel numbers and the kernel sizes of all layers, to meet the requirements for the real-world applications due to constraints such as the latency, energy, and also accuracy. So to solve this issue, we come to the third part of this talk, 3D network design. We introduced the 3D neural architecture search to automatically design efficient 3D models. In order to do so, we first designed a large search space that covers a wide spectrum of 3D models. So basically, we include network architectures with different network number of channels and also different network depths. As the size of the design space is very large, which is actually larger than 10 to the 40s, it is not feasible to train each candidate network from scratch. So therefore, we decouple the training and the search stage. We first construct a large super network where all the candidate networks can be seen as its subnetwork. For example, if the network, the number of channels of the first layer can be 1, 2, 3, or 4, then the first layer in the super network will simply have the largest number of channels, which is 4. By doing so, all the candidate networks with fewer channels can be cropped from the super network by simply choosing the first several channels. We can also do the same thing for the network depths. During the training stage, we randomly sample a candidate network from the search space and only optimize that portion in the super network. However, we found that with only weight sharing and uniform sampling, the layers are not equally trained. This is because even if you are sampling to use, let's say, only like 3 layers, the first layer will also be optimized. Therefore, the shallower layers will be trained more compared with the deeper layers. To tackle this issue, we proposed the progressive depth shrinkage. It breaks the training iterations into several segments. In this particular example, we assume that there are only 3 depth choices, 1, 2, 3, and 4. Oh, 1, 2, and 3. In the first segment, we are training the full network, or equivalent, we can say that the network depth of each stage is only allowed to be 3. In the second segment, we allow the network depth of each stage to be either 2 or 3, each with 50% of probability. And in the final segment, the number of blocks for each stage can be either 1, 2, or 3, sampled from the uniform distribution. By doing so, the deeper layers are compensated and trained more sufficiently. So after the super network is trained, we then run the evolutionary search to find the best candidate network given a specific computation budget. During the search stage, we can directly grab the weights from the super network without retraining. This actually greatly saves the search cost. We found that our training and search process takes roughly the same amount of training time as training like a single network, which makes the search process itself very efficient as well. The whole 3D NOS pipeline is very complicated as it needs to deal with a vast design space. Therefore, a natural question would be whether it is necessary to support such a fine-grained search space. Recently, researchers from Google claimed that it is possible to find efficient 2D neural architectures by simply scaling the network widths, depths, and resolution jointly. However, we found that this compound scaling approach in 3D is not as effective. We believe that this is because there isn't any well-designed 2D models like the mobile net to start with. In 3D, we found that even the state-of-the-art Minkowski net is not very well tuned. Here we break down its computation and found that it is extremely unbalanced. Over 75% of its computation is concentrated on the decoder, and in fact, most of them are actually on the final decoder stage. Intuitively, the encoder stage should be like at least equally important compared with the decoder, which suggests that this unbalance might not be a very good design. If we only scale the model uniformly, this imbalance will still be there. Therefore, it is necessary to have a diverse search space. With our architecture search, the best model we found has a much more balanced encoder-decoder ratio, and it also achieves much better performance, which you will see in a few minutes. Another possible simplification is to only search the channel numbers of different layers. In 2D, it is possible to achieve very good performance by doing this. However, this is not the case for 3D. By reducing the number of channels in Minkowski net by half uniformly, the theoretical computation is reduced by 4 times as expected, as the computation cost is quadratically related to the number of channels. However, the reduced model is only 1.1 times faster than the full model measured on the GPU. This might be because 3D sparse kernels are usually bottlenecked by the memory movement rather than the matrix modifications. This warns us that simply scaling down the channel numbers in 3D is not sufficient for us to obtain models with very low latency on real hardware. And the elastic network depth is indeed needed. In our design space, we are supporting different channel numbers and network depths. However, we are not including the large kernels into the search space. This is a little bit counterintuitive, as in 2D, we usually found that large kernels might be very useful. For example, like in proxies with NOS, the search architecture has many 5x5 and even 7x7 kernels being used. A single convolution with large kernel size might be more efficient than multiple convolutions with smaller kernel sizes, because it reduces the number of kernel calls and also better utilize the hardware parallelism. However, large kernels are not preferred in 3D. After analysis, we found that one convolution with kernel size of 5 requires more than 2 times of the computation compared with 2 convolutions with kernel sizes of 3. Even worse, when we analyze the cost for kernel map construction, we found that building kernel map for a kernel size of 5 is roughly 5 times more expensive compared with the kernel size of 3. This is because we now have to query 125 positions for each output point, while we only have to query 27 positions when the kernel size is 3. Based on these observations, we're now using large kernels in 3D and stick to kernels with size of 3. Another major difference between 2D and 3D is that we are facing data sets with much smaller sizes. For example, the largest available 3D segmentation data set is semantic kitty, which contains around 20K training scenes. However, in 2D image recognition, ImageNet dataset contains over 1 million images, which is 67 times larger. Fewer training samples translates into fewer training steps and also fewer architectures being sampled. In 3D, we found that the super network is not sufficiently trained, as there are not enough candidate networks being sampled during the training process. Different from 2D NOS method, where the same candidate networks is sampled on different GPU workers, we sample different candidate networks on different GPUs and aggregate their gradients during the backward propagation. This can be simply implemented by setting the random seeds on different replicas different. We named our sampling strategy as heterogeneous sampling and the vanilla one as homogeneous sampling. With this very simple technique, we found that the super network trained with heterogeneous sampling offers a much better trade-off curve, achieving more than 1% better under all computation budgets. All right, this concludes the approach section. To briefly summarize, we first designed PVConv and SPVConv as efficient 3D building blocks. We then optimized the sparse convolution to enable faster inference on the general purpose hardwares. And finally, we introduced 3D neural architecture search to explore the best 3D model given a computation budget. Now let's switch to the experiment section. We have evaluated our model on 3D object part segmentation on the ShipDev part dataset. This task is basically to segment the 3D object into its functional parts, for example, segmenting a table into its legs and top. Here we compare with a bunch of other 3D models, including PointNet and PointNet++, as well as PointCNN. We can see that our PVCNN achieves a much better accuracy latency and accuracy memory trade-off compared with all these baseline models. It is 2.7 times faster and consumes 1.5 times lower memory than the state-of-the-art PointCNN. It can achieve real-time performance on lightweight edge devices, including Jetson Nano, which only consumes the energy of a light bulb. On slightly more powerful hardware such as Jetson Xavier, it can process more than 100 objects per second, which is roughly 2 times faster than the previously fastest model, PointNet. We then evaluate our method on 3D indoor semantic segmentation dataset, and we can see that the improvement is even more significant. PVCNN++, which is built upon PointNet++, outperforms PointCNN with roughly 7 times speedup. And here we compare with the previous fastest model, PointNet. Our PVCNN is roughly 2 times faster. It is also more accurate. In the first example, we can see that the PointNet misclassified the desk as the chair, while our model gives the correct prediction. And finally, we have also conducted some experiments on the 3D outdoor scene segmentation dataset Semantic Kitty, and our method is currently the leading solution on the Semantic Kitty leaderboard. Here's a live demo comparing our SPV NAS against the previous state-of-the-art Minkowski net. You can see that our model is roughly like 3 times faster than the Minkowski net and achieves a throughput of 9.1 frames per second. So we demonstrate the results of our SPV NAS. You can see that we can achieve 8 times computation reduction and 3 times measure speed up compared with the Minkowski net while achieving higher accuracy. This allows our model to be more efficiently deployed on the real self-driving cars. As our solution contains a better building block design as well as a better architecture design, the natural question would be how these two contribute to the final performance. Here we break down the improvements. The gray line is the vanilla Minkowski net. And by replacing the sparse convolution in Minkowski net with our PVConv, we improve the trade-off curve from the gray line to the green line, achieving up to 2% IOU boost under all computation budgets. We then further boost the performance of PVCNN using the 3D NAS, which lifts the trade-off curve from the green line to the red line with up to 5% improvement under the same computation or latency constraint. Here we can see a huge improvement, especially when the results constraint is very tight, as we also want to understand where the improvement actually comes from. We visualize the predictions of our SPV NAS as well as the Minkowski nets. And we observe that fewer errors are made on safety critical small objects and boundary regions. So to verify this, we also provide some quantitative results on these more instances. And we can see that our SPV NAS achieves 5% to 25% IOU improvement over Minkowski net on these small instances. This will potentially make our SPV NAS model much safer when deployed on the real cars. And finally, we have also compared our SPV NAS with 2D projection-based methods. While achieving 3% to 10% IOU improvement, our SPV NAS reduces the computation cost by up to 58 times and the model size by up to 46 times. Here's a demo comparing our SPV NAS with projection-based darknet. You can see that our SPV NAS achieves over 10% IOU improvement, and it actually runs at 11.2 frames per second, which is faster than the frequency of the LiDAR sensors. I will then showcase one real-world deployment of our efficient 3D models. Here you can see that see the video of the autonomous racing vehicle of MIT Driverless running on the track at the Formula Student Germany competition last year. The goal of the computation is to build an autonomous system to drive the car along the track fast and safely without hitting any traffic cones. There are blue and yellow cones on the track to mark the drivable space of the car. Therefore, the LiDAR perception system is required to detect and classify the cones. Together with engineers at MIT Driverless, we have deployed our PVCNN model onto their car and replaced their original pipeline. This is a video demo comparing the performance of MIT Driverless pipeline and our PVCNN. You can see that their original pipeline is often quite unstable, and the inferred color is shifting between the blue and yellow frequently. The accuracy of their pipeline is only 95% with 8 meters of safe perception range. This can also be seen from the bird's eye view where the cones are not detected until the car is fairly close. With our PVCNN, the car is able to classify the cone faster, which with almost like perfect accuracy. The perception range is also extended to 12 meters. This allows the car to see further and drive faster and safer. Here's another video demonstrating the performance of PVCNN on the driverless vehicle. Note that although we have the visualization of the stereo cameras, they are not used during the inference, and the car in this video is still driven by the LiDAR perception only. And we can see that equipped with the PVCNN, the car drives pretty smoothly on the track. To conclude, efficient 3D deep learning is a very important yet fairly underexplored direction. Our preliminary explorations demonstrate promising performance on 3D object indoor and outdoor scene segmentation. And by the way, we have released the code base as well as the library on the GitHub. So feel free to try out if you're working on the 3D deep learning or related stuff. Thank you so much.